Get started in just a minute. Let everybody sit down. Okay, my name is Jim Radigan, and my colleague is here, Don McGrady. He's going to be talking about AMP. I'm the dev lead for the optimizer team for the C++ compiler, and Don leads the C++ AMP team. And what we're going to try to talk to you about today is all of the performance tools that we've created for Visual Studio 2012. And the title of the talk is It's All About Performance. So they don't let us out of the basement too often. We're down in the compiler team. So if this gets a little dense or this is a little dry, just throw a hand up and be happy to answer a question, okay, along the way. So they asked me to write a mission for what the talk was going to be about. And this is what I wanted to really get across. It's really important to go under the covers, to take a look at the hardware that's out there today and really understand it so that when you're programming, you understand what there is to exploit. And once you understand that, you'll understand then how important the tools are that we're providing for you in Visual Studio 2012. So basically, we're going to go span a continuum of the tools. We'll look at PPL, we'll look at AMP, or basically, we're going to look at how you can do nothing. And that's basically using the C++ compiler, the new one that we're putting out right now that has auto vectorization and automatic parallelization. How many people remember the Pentium? I'm getting old, right? So everybody remembers this. This was a big deal, right? Everybody was, wow, 3 million transistors, right? Well, and I remember I was on the compiler team at Intel at the time. It was a really big deal. There were at least 6 team months getting things straight so we could actually do 2 things at a time. Remember the U and the V pipe? That was a big deal. Bottom testing loops, being able to actually get things aligned. Well, here we are today, right? That's 1.4 billion transistors. That's Ivy Bridge. I couldn't believe it. It's in a laptop downstairs in the hall. It's the ASUS ZenBook. There's the Pentium, right? So now if you were to use the same semiconductor technology that Intel has today, that little black dot right there, that's the Pentium. That's how much it shocked me when I actually did the math to try to make this PowerPoint slide, how much it's changed. Right? And now, here's the key point for the talk. All of this space here, every bit of that except for the part that's cache, is controlled by the compiler. Or it's controlled by you through the tools. And I'll show you a functional block diagram, but all of that's available to you now on chips in laptops that are $1,000. And that's just this year. So if you're looking at the Surface device, that's the chip that's in there. This is the Tegra 3. It's not quite at the same semiconductor process, but it's 5 cores. Each one of those cores has 128-bit vector instructions, just like the Intel parts and the AMD parts. But the little different thing here is that this extra core is the low power core, and it'll work at 500 megahertz and save power when it's in the idle loop. So one of the things that's really important is you want to go as fast as possible so you then get back into that idle loop. I thought this graphic was a great one for the common adage that we have now about speed really does get you power. The sooner you end your app, or the sooner you end the compute-bound part, for example, of your application, this chip will take it off those 4 cores, and then it'll run the one thread on the low power 500 megahertz half speed core. So really, this is what it's all about. You keep hearing us talk about going native, going native. This is the C++ renaissance, and it's really about exploiting the hardware. So that's the functional block diagram of the Ivy Bridge part that I showed up in the 2 slides back. As you can see, it's 4 cores. Each one of these cores has 256-bit vector instructions. The instruction set's really rich. There's a lot of stuff in the instruction set for just handling control flow. So vectorizing integer codes now is mainstream technology. Any compiler that's actually compiling for modern hardware has to have a vectorizer. Okay? And this, of course, is a huge amount of hardware that's now on chip sharing this cache for the graphics. And that's what C++ AMP is going to exploit. So if you think about it, there's a lot available to you if there are parts of your applications that are performance critical that you really, really want to take advantage of. So what I'm going to talk about really is a different visual of how important this is. That red arrow really, really matters. That's what I'm trying to get across here, is that we map this platform onto this platform. And if you want to know how much it matters, in the last 5 years, I just got this off the radio from Bloomberg, $87.7 billion was spent on Windows licenses alone. And then if you put all of the money that was spent on AMD parts or Intel parts or ARM parts, you're well over $100 billion. So that red arrow really, really matters. And so what I'm going to try to do is talk about the red arrow in a way that makes sense so that you can walk out of here with a little bit of knowledge and a little bit of an understanding so you can go take advantage of the hardware. So I'll go briefly into a little bit of computer architecture. I'll talk about the auto-vectorizer and automatic parallelization that we put into the C++ compiler for Visual Studio 2012. Talk about PPL, because we can't get it all. And then Don's going to come up and he's going to talk about AMP. So I'm going to bust into the hardware part right now. I'm going to talk a little bit about computer architecture. I'm going to try to make this really accessible. You don't have to remember any of it in great detail, just the general concepts so that you know what's going on when you're actually worried about the performance that you're trying to extract in critical loops. So I'm going to talk about what does superscalar really mean, and this is going to be an important insight that you can exploit for runtime dispatch. I'll talk about vector instruction sets. I'll talk about being vector and parallel. And then I'll talk about what SPMD means, single program, multiple data, which is really a description for the architectures that are commonly referred to as GPUs. All right, this, at its heart, is in Nehalem. And what you'll see is at one clock tick, you can literally do 6 things at once. So there's an enormous amount of instruction-level parallelism going on under the covers for you. And it's really, really difficult to find that much instruction-level parallelism. So you can say that there's an enormous amount of data by compiling all of the code inside Microsoft. And what everybody has found is that about 20% of the instruction-level parallelism resides within a single basic block. The next 60% is across two basic blocks, and then the rest of it is scattered throughout the rest of the program where you have to do like really serious code motion. So in order to get 80% of the instruction-level parallelism, the architecture needs to be speculative. And bear with me for a minute, and I'll explain why this is important to understand. But these are 2 disjoint pieces of code. This ends at address 145. That ends at 188. And if you look at the causality chains in this code, there isn't a lot of instruction-level parallelism there. And there sure as hell isn't a lot going on between these 2 when you consider that there was a branch in there, right? Well, what the hardware does is it will actually speculatively execute the red operations. And then once the branch is executed, it'll put the red operations into the visible architectural state for you. Okay? And that's what's going on now, and that's how you can feed a 6-wide superscalar machine. And this is really important. So once that executes, the hardware realizes that the right-hand side can go visible. Okay? If the architectures didn't have that capability, it would really thwart being able to productively vectorize general-purpose C++. And I'm going to explain why. And these are two tricks that you might want to use in your applications. So that's a typical C program, right? You're passed in 3 pointers. You have no idea what they point to if you're a compiler, right? And you've got to be correct all the time. You also don't know what instruction set you're going to be targeting. But this might be pertinent for your applications. So let's say that we wanted to go to the SSE 4.2 instruction set. What we've done is we've put a global variable in the CRT so that at startup time, you can actually runtime test what instruction set's going to be available for you. Now, remember that these are passed in, and we have no idea what they point to. They might overlap, right? A might point into a little bit of B, or C might point into a little bit of A. So you got to do a runtime check or runtime disambiguation to see if any of those aggregates possibly overlap. And then, okay, and then you can two-version the loop. So if the instruction set's available on the architecture that you want, and all the pointers are not overlapping, you can go to the loop really quickly. But if you remember now, people are worried about what does this do for performance? What's the latency for all this runtime checks? Well, I just showed you the superscalar architecture really almost pretty much makes that go for free. And we've got loops where we've got tremendous speedups that I'll show you shortly, where the size of this is 34 predicates, and we get like 50% speedups. All right, so that's superscalar, and that's why that's important. So now I'm going to talk about vector. That's a graphic for a simple vector instruction. That's an add packed single. So that's 32-bit floats, 4 at a time. So in one cycle, you load all 4 of one operand, you load the next 4, and then you do the add, and that's 3 cycles. So clearly, if you can actually do 4 things at once, legally, that's a big speed up for whatever you're programming. So everything now should be looked at as the scalar unit and the vector unit. Those are traditionally how we refer to them. So everyone's used to one 32-bit operation at a time, and now with the vector units, it's kind of a 4 for 1, 8 for 1, 16 for 1. Okay? And that's a graphic to realize the power of each one of these cores. I showed you the 4 cores on Ivy Bridge being scalar and vector. So if you're doing 4 things at once on this, and you multiply that by 4, if you can get the thing to go parallel, then you've got 16 things in one cycle. All right, that's vector and vector parallel. This is GPU. So the idea with the GPU, which was that part of the chip on the far left-hand side that we were referring to as SPMMD, is that you've got 32 really, really simple cores clustered in these different, they call them different names, but in this, we're calling them a multiprocessor in this graphic. And the idea here is with each one of those tiny, simple cores, there's a program abstraction, which is each one of those simple cores is going to run a simple thread, and each thread is going to get a thread ID. So this code on the right is a general abstraction for the fact that you would load based on your thread ID, you do the computation on your simple CPU, and then you do the output relative to an address calculated by your thread ID. And now the idea with the SPMD is you've got thousands of these little threads. And this is the idea that C++ AMP exploits for you. Okay? So we talked about the hardware, and now I'm going to go on, and we're going to talk about Vectorizer. So in 2012, we took the C++ compiler, which is probably parts of it 18, 20 years old, and we really tore it up and put in an automatic vectorization capability and automatic parallelization. And in order to properly cover this topic, I'm going to go through superscalar, vector, and vector parallel, which were the hardware architectural features that I had just covered, okay? So here's a simple example. If we take this C++ loop and we automatically vectorize it for you, that's what we'll generate on the right-hand side. I know the Intel guys are in the crowd. They're probably wondering why I didn't use the optimal instruction sequence for this, but this is good for mapping it in a simple way. So here we go. We're going to load 4 things at once, load the other 4. We're going to add them, and then we're going to store them back. So what's in point here is that the compiler has to look across loop iterations in order to figure out if it can do this legally and bring computation back. And that's an important thing for you to understand if you're going to write something that's going to go parallel, or if you're going to try to write something that you want to go vector. Okay? You've got to be able to look across iterations, determine if you can aggregate things, and see if it's legal. You can do this by yourself, by hand, right? These are the old intrinsics that we supplied. But the problem with this is that you bind to a particular architecture, and if this is, supposed to be C++, a lot of people call that Klingon after you've written a huge complex loop in these intrinsics. It's really, really difficult to understand. So in order to understand this, the vector semantics are all loads before all stores. And if you just keep that in your mind when you're writing an application and worrying about going parallel or worrying about going vector, you'll see that that actually turns into something that maps naturally onto a mathematical problem. So bear with me on this. This is the only part that's going to have math in it, but this is core to understanding whether something's legal to vectorize or go parallel. This is a sequential loop, a little tiny simple one, and then this is what would be considered the vectorized version. That's like a Fortran 90 syntax there. Like load those 4, add them, and then store them. Semantically, these are not equal, so it's not legal to vectorize this loop. So if you want to think of it concisely, look at the difference between how A sub 3 is calculated in both of these loops. So in this example here, that red arrow shows that there's what we call a flow dependence across loop iterations. This store is going to affect the next iteration where it's going to be read by this operand. And I'll show you this. So if we did the vector version of this, you'd load those 4, you'd load those 4, you'd do an add, and you'd do the store, and you'd see that A sub 3 is really a function of A sub 2 and A sub 4. Seems pretty straightforward, right? So now, if you go back to the sequential loop, that's how it would actually execute, and you see A sub 3 is a function of all of those. So you can see semantically, A sub 3 would not be converted equally. So that whole arrow back there, that red arrow, is an abstraction that the compiler has painstakingly engineered into its analysis. So that I and that I are meant to be induction variables of the loop at different iterations. And this, I'm not going to go into this much further, but the key point I want to get across is that we doubled the size of the optimizer in Visual Studio 2012 to do the analysis that would automatically vectorize and parallelize things for you to avoid the incorrect mapping that I just showed in that previous example. And that simple concept is all you have to walk away with, though, if you want to do this by hand or if you want to understand why things aren't working for you, if you just make things go parallel without checking. Okay? So it gets hard, though. I showed you little simple examples with array references. This is the n-body. This is the code for n-body simulation. And you can see that this is a little, the C++ in here is starting to get a little bit complex. And so a huge part of the compiler and what you're going to have to deal with is that C++ has complex memory references. And so oftentimes we won't be able to vectorize it for you, or you won't be able to figure it out, because if you're using templates and meta-level programming, it's really hard to understand what represents one memory reference on one loop iteration and what's the next. So it's hard. So what we've done is we've given you two switches. QVecReport:2 will tell you what are the loops we didn't vectorize, and will give you all the reasons why, so you can go and modify the code. And then we also have another one for the parallelizer. And the number of reasons are all documented on MSDN, I think, as of last month. So that's doing 4 things at once. That's doing 8 things. That's doing 16 things at once. So we'll do that for you automatically, and here's how. We've introduced a new pragma. All you got to do is decorate this loop with a hint. Automatic parallelization is on by default, but a lot of times it's not profitable. This will tell us that you think this loop is profitable to parallelize, and you want it to run on 4 cores. Okay? So what we're going to do for you is we're going to take the body of this loop, we're going to outline it first after we've vectorized it, and then we're going to call a library function with new parameters and basically that function pointer, which is the code that we have vectorized. Okay? And this will happen for you automatically. This is very akin to the vectorizer creating a lambda for you, right? And shoving it into a library call. This is what goes on at the assembly language level. If you dump the ASM files, you'll be able to see this.
Does that override the protection that you were talking about before? That fragment would it automatically parallelize regardless?
No, that's a really good question. So that's why we struggled with this syntax. When we say hint,
Repeat the question, please.
oh, the question was, the gentleman asked, if you put this pragma in here, will it basically parallelize, will the compiler parallelize this even if it's illegal, even if the analysis that I just showed you wouldn't make it, would prove that it's illegal? And the answer is no. We'll actually go and still do the full analysis, and we'll try to parallelize it, but we will never do it if it's unsafe. And that's completely different than if you use the PPL constructs, where you just say, make it go parallel. And we'll actually tell you, you'll see the report saying that we didn't parallelize it for certain reasons with the pragma. And so then what happens is at runtime, that's what you'd see. So each one of these guys is running basically in vector mode. So coming back to the bigger picture, right? Now you've got, so in Dev 10 or Visual Studio 2010, we were only lighting up these 4 squares, and now with 2012, we're taking all of that real estate. And that's something that you can do with your applications. So here's a demo to compare and contrast. That's a sequential loop of the n-body's code that I showed you. And then what we're going to show is that sequential code running in parallel. And if you look at it, I think it's running at about 22 frames per second. And now with 2012, that's one thread vectorized, and it's already as fast as the parallel version in 2010. And that's vectorized and parallelized. And so this visual is something that can make you feel the kind of speed up you can get with a 4-core. And the 4-core machine is pretty prevalent already today. And in a minute, I'll show you some demos with 32 cores. So I'm going to diverge for a second. We're not doing Fortran. We spent a huge amount of time trying to advance the technology. This vectorization and automatic parallelization is pretty mature, but we spent many man years trying to do C++. And so this is a great example of Spec2K6 Hummer. This is an integer DNA sequencing programming. And nothing in here is floating point, and there's all that control flow. And we'll vectorize this. So what we do is we go in and we recognize that backward flow dependence that's similar to what I showed you in the very beginning. And what we'll do is we'll distribute the loops like this. And then that blue if at the bottom can actually be optimized away because it's a function of that loop induction variable. So we'll get rid of that. And now what's critical is you see all of these red ifs. Really what they look like is a min or a max, you can imagine, right? Now, wouldn't it be great if the vector hardware had a min or a max instruction? You could get rid of all this control flow. Well, what the compiler will do is it'll actually recognize a whole bunch of idioms for max and for min and whether they're nested. And it'll map them onto an abstract function, which we then map onto the hardware instructions. So the 4.1 instruction set for SSE2 has a max instruction, and it's similar to just like an add. You load 4 things at once, and then you produce the max. So what happens then is we're able to get rid of all that control flow. We're able to then wrap this loop with all the runtime checks that I talked about with no big impact to the latency. We'll see if the 4.1 instruction set's available, and then for this loop, we have to check every store against every load for about 38 different runtime alias checks. And this loop will then speed up on one core 50%. So we'll run that loop vector, we'll run that scalar, and we'll run that loop vector. So we also, in 2012, added a vector math library. So it turns out that if you want to draw, and thanks to Juan, if you want to draw the ocean waves, you need the sine function. So that's a little bit of a summary for what the loop looks like for the program that you saw drawing the ocean. And what we've done is, in the compiler, we've extended the instruction set so that we can target a short vector math library sine function as though it were a hardware instruction. And this is available to you. So that would turn on to a vector load with the normal hardware instructions, and that would turn into a runtime library call. So you can vectorize loops that have all the transcendental functions. So that will vectorize 4 things at once, and underneath it's been tuned highly for being able to get the most performance on the Intel parts. The parallelizer and the vectorizer are both on by default. If this is a compute-bound loop, then we will parallelize it for you, if it's legal. It turns out in the world that there aren't many easily identifiable compute-bound loops, so that's why we came up with the pragma. Okay? So the pragma is a simple directive. It couldn't be any more simple, I don't think. And then if the pointers escape or there are procedure calls or we can't figure out whether or not the alias relationships between all these disprove overlap between iterations, we will not parallelize that for you. So one of the things that's important too, in addition to parallelization, is scheduling. You know, if you just divide something up into 4 equal chunks, that isn't always the right thing to do. So you need some notion of static scheduling and dynamic scheduling. And this program is a great demo for showing the differences between static and dynamic. So this is the core compute-bound loop in this thing, which actually is concerned with drawing and blurring these reflections, and that one, and that one. And what you'll see is the bounds for these loops are variable, right? So as the ball is bouncing, the blur gets moved around and the amount of work that you're going to do changes. And so if you had chunked this up and went 32 cores and everything, you just split it up into 32, you wouldn't get full machine utilization. So let me just show you this demo. So on the right, you can see the CPU cores. This is a 32-core machine. This is something you want at home. So there's one core floating around with a little bit of parallelism through PPL. And then that's the best we could do with Dev 10 or Visual Studio 2010. So now this is (2012), and that's with the ball now vectorized. And then this is the ball vectorized with a dynamic scheduler. It'll actually dynamically move threads around and change the number of iterations per thread. And it's pretty smooth. There's a lot of computation going on here. So you can see what we did to a 32-core machine with that. I think somebody else is on the machine too, because usually this is a lot faster. I told everybody that my team is trying to get a deadline, so they're on there, I can tell. But the point is, there's dynamic scheduling going on here for 32 cores. And you get that actually for free with the Visual Studio 2012. We'll vectorize that loop, we'll automatically parallelize it, and then by analyzing that loop, we'll select the scheduling strategy. I don't know who he is. I really don't. All right. So that's enough about the vectorizer and automatic parallelization. Hopefully you can take some of the stuff that I talked about and actually start to read a little bit and look on MSDN and see some of the details. You really want to take advantage of the hardware. There is no magic bullet, though. You can see that there are issues with legality all over the place, and C++ is very difficult to analyze. And so what we've done in Visual Studio 2012 is we've built a continuum of abstractions for you to exploit. So what I'm hoping you can see is on the far left, that's the little vector add that we've been talking about for most of the time. If you want to use PPL, and because for some reason we didn't parallelize this, you could change your abstraction and use a parallel 4 with a lambda. And then if you really want your add to go fast across a huge problem space, you can go on AMP, and you can use this abstraction, where you then copy it back to the CPU. So this was the best way I could think of to show the continuum of abstractions that we've built in Visual Studio 2012. You can insert your computation into the appropriate loop. Okay, you just have to figure out whether your black box fits in which abstraction. So the C++ compiler, there's one other thing I want to mention, though, and not many people understand it, but if we don't, the vectorizer that we built in 2012 is V1, and it's on by default for x86, x64, and for ARM. And it's used inside the company to build all of this software. And so we can't check in until we actually prove that each one of these things works correctly and it gets passed through the stress lab. So if it's on by default, there's a lot of stuff that we have already written for the next version of vectorization, or the more aggressive vectorization and more aggressive parallelization, but we have to be extremely cautious because the number one thing that we hold valuable is correctness. And then because Windows builds us, we're used to build Windows every night, the second thing is compile time. So we can't advance the technology as quickly as we would hope just because we have to remain 100% mission critical correct. Because when these teams get a bug, it is a serious lifestyle choice if you're a compiler guy. So this is PPL, and this is why I think PPL is a great addition to everything that we're doing. It allows you to, if we can't figure it out whether it's legal or not, you can just go ahead and manually say, I want something to go parallel. And it goes, it's three simple constructs, and they give you a huge amount of value, especially since everything is multi-core these days. So that maps onto an ordinary C for loop, right? You got a lambda function that takes one parameter. It's the I that the parallel for will iterate for you, 0 to 100, and the stride is 1. That's really straightforward. Now, if you use STL, you can actually get a little bit more fancy, and you can use the vector iterators or the STL iterators using a parallel for each. And then finally, if you just want to fling a couple of functions over the wall and make them go parallel, you can use the parallel invoke. Now, scheduling matters, and PPL has an underlying scheduler which actually does what they call dynamic range stealing. And the way they've engineered it is really pretty good. It's very scalable, and it supports a low task granularity. And it really gives you a lot of bang for the buck with a very simple source change. So one of the things I'll show you now is Mandelbrot. And as you can see, a core part of the computation here is an if-then-else, right? So if you go through here, there's a small computation. If you go through here, there's a lot more computation. So that means if you want to go parallel, the threads are going to do a different amount of work or spend time on a core that's different. So I showed you the inside of this. So if this was the original C code, you could parallelize it very trivially just by wrapping it with a parallel for and a slight rewrite. And it's almost identical. And then this guy is going to actually do the right scheduling, a generic work stealing for you. And so let me just show you that demo. So here's what that code looks like without, this is the runtime, what that looks like without PPL. 1001, 1002, you can feel that, right? Now, if you want to run that on 32 cores, just by throwing that simple parallel for construct in there, this is what it feels like. It's a radical difference. And then you can just drill, if it matters, you can drill down really quickly. So that's a pretty big change, right, for a very simple construct. So what I'm going to do now is I am going to turn the rest of the talk over to my friend Don, and we're going to move on to AMP, which is the last part of the continuum that we wanted to talk about.
Thanks a lot, Jim. I appreciate you giving me 10 minutes to talk about C++ AMP. So while I'm talking to this, I'm actually going to bring up the lights, because before I do that, I'm going to do a little demo. So if and you guys are going to be part of it. So I've got a webcam here, and I'm just going to show you this little demo starting with multiple cores. So I'm not even going to show you the single core experience. So just in a nutshell, what this demo is doing is it's taking images from this camera and it's doing some math on them. It's finding edges, it's finding areas between those edges, and it's finding an average color, and it's painting them with this average color, so it gives a cartoonized effect, and that's why we call it a cartoonizer. That's what the demo is. And this is running on my laptop here, which has 4 cores. And it's a little jerky, so it's really not getting me the experience that I want. It's not something that I would be proud of if I was going to ship this. But it's a data parallel problem, so that means if I can throw more cores at it, it should run faster. Now, I could run it on that 32-core machine that Jim showed you, but I'm willing to bet none of you have 32-core machines. That's too bad. But you probably have 4. There's a reason why you don't have 32, and you probably won't in the near future, and that's those cores are running pretty hot. They consume a lot of power, so if you add more of them on the chip, it's just going to cause more power to be consumed. So the trick is to run them on many more lower power cores, and those are the kind of cores you see in the GPUs that you might already have in your system. This laptop has a NVIDIA Quadro 2000. I think it has about 96 cores, and each one of those cores has wide vector lanes similar to what Jim talked to you about too. So just to whet your appetite to what you can expect if you do that. Now you can see, you're not even dropping the jitters from my hand shaking, so you're not dropping any frames. And the key thing to note here is that the demo here that I'm showing you is a modern UI, a modern Windows 8 UI. So C++ AMP is just part of C++, so it works with everything that a C++ can do. So I'll bring the lights back down to presenter mode. I came back to this diagram, which you've seen before. It's the Ivy Bridge processor, to talk about what C++ is designed to do. And in a nutshell, what it's designed to do is let you exploit the full computing power represented in this picture. And you've heard Jim talk about how superscalar optimizations and instruction scheduling can get you great serial performance on each one of those cores, and how the vectorizer and the automatic optimizers can exploit the vector units on each of those cores, and how the auto-parallelizer and PPL can exploit all the multiple cores at the same time. But in this example, 30% of the space on this chip is the graphics processor. And up until now, no single language lets you exploit everything on this picture. If you wanted to exploit the graphics processor, you had to switch to a different language like CUDA or OpenCL. So finally, with Visual Studio 2012, there's one language, the Microsoft C++ compiler, that will let you program this entire chip. So what's C++? I'm just going to read one bullet, and that's this bullet. It's a programming model for expressing data parallel algorithms and exploiting heterogeneous systems using mainstream tools for productivity, portability, and performance. But most importantly, the most important 3 letters in C++ AMP are C++. I want to get across to you that it's just C++. We light up the GPU with a simple language extension and a supporting programming model in the form of a library. And because it's just C++, it's part of Visual Studio 2012, which means it works with those other great technologies like the modern Windows 8 UI that I just demoed. And you get a great editing experience with colorization and background compilation and IntelliSense and debugging and everything that you'd expect to get just because it's C++. So we think that's really key. And what does C++ AMP give you? Well, I hope my demo stressed that it can give you a lot of performance if you have a lot of parallelism to exploit. But it does give you that very productively, as I'm going to show you in the next few slides, with a very approachable, simple programming model with few new concepts that I hope would encourage you to experiment, wade in quickly and try some experiments without having to overcome a huge initial learning curve. We give that performance to you with portability because we build on top of DirectX 11. And if you have DirectX 11 capable hardware from NVIDIA, AMD, Intel, and soon ARM, it'll just run there. C++ AMP is also published as an open specification. And that means that we actually encourage other vendors, people who produce C++ compilers, to actually produce a C++ AMP implementation. And we're very hopeful that they'll start doing that. And finally, of course, you get performance. As I showed in my demo, it's the one thing now in C++ you can exploit all the performance that's available to you in your hardware. So now I'm going to show you a little bit about what this programming model looks like in the form of a Hello World program, as you would expect. This is Hello World. There. I have my string here in this array. I'm going to do some super complicated math on it. I'm going to add 1 to each of those characters, and by the time it gets printed out there, it's going to be Hello World. And this is running in serial, and I'm going to take you step by step to bring it to the GPU. If you want to use C++ AMP, you include the header file and use the namespace. Most importantly, and I'm going to circle back to this, you need to tell C++ AMP what data you're going to operate on. And the way you do that is with this concept called an array view. So I have my data, my array V. In order to tell C++ AMP about it, the way we say to do it is wrap it in an array view type. Now this doesn't create any new memory. All it does is tell C++ AMP about existing memory. And now if I modify the rest of this program, everywhere I was referring to V, I'm now going to refer to AV. This is still a correct program, but we're not running on the GPU yet. This is still a serial program. Now if I want to run it on the GPU, I need to replace that for loop with a for loop that's going to run on the GPU. And we call this parallel for each. Don't let the name fool you, it's just a for loop. Now if you think back to the original serial for loop, it went from 0 to 11 counting this variable called IDX. So now you're asked, where'd the 0 go? Well, in C++ AMP, all loops start at 0. So that's a simplification right there. And now where'd the 11 go? Well, the 11, I put it right there as the extent of the array view. So the parallel for each operates from 0 to that extent, in other words, 0 to 11. And now the loop body I replaced with a lambda, which you saw in previous examples. And the function, the loop body, takes as its parameter the index. And notice that it's an index of rank 1. We actually support 2-dimensional array views. 3-dimensional array views, n-dimensional array views, doesn't matter. For example, if I made a 3-dimensional array view, my extent would be a 3-dimensional extent, and it would mean go from 0 to, the extent in that direction, 0 to the extent in that direction, and then 0 to the extent in that direction. And the index you would get there would then be a 3-dimensional index. Finally, restrict-amp is the one major language extension that lights up the GPU, and it does 2 things. First of all, it says, this loop body, I want you to generate code for it differently. I want you to generate it to go to the GPU instead of the CPU. Secondly, it enforces a set of restrictions within that function scope. Now, GPUs today are capable of running a large subset of C++, but not full C++. So restrict-amp restricts that loop body to a subset of the language. In particularly, you may have wondered why I said int here for my array of characters, and that's because the platform we sit on top of doesn't work well with characters. So I have to use ints. If I had put character in there, I would have gotten errors from the compiler in here because I said restrict amp. And this is good because you don't have to wait until you compile it and run it and get a unspecified failure or undefined behavior when you run it. You find out at compile time. Finally, let me circle back to these array views because they're key. Typically in a GPU, well, maybe not typically, but I still recommend people think about the memory that the GPU can access versus the memory that the CPU can access. Because with a discrete card, you have your CPU memory and your GPU memory, and if you want to operate it onto the GPU, you need to move data to the GPU. And when you want your results, you need to move it back. So array views handle this automatically for you. They're really smart. Here on line 10, or actually when it's captured on line 8 into the lambda, the array view says, hey, I know that the latest version of my data is on the CPU. It's not on the GPU yet. So I'll automatically move it to the GPU at that point. I'll do my computations on it. And then on line 13, ArrayView gets accessed, but it's smart, and it says, hey, I know that the most recent copy of that data is on the GPU, so I need to move it back to the CPU and wait, if necessary, for that parallel 4 to finish executing. So it all happens automatically for you. As a programmer, you need to be aware of it, because if you are moving a lot of memory around, it's going to impact your performance. So I hope this is actually, this is the programming model right here. It's the same programming model, the same technique that I used to speed up that cartoonizer that I showed you. And I hope you can appreciate how simple and approachable that is, and I encourage you to play with it and try it out for yourself. Just quickly, I want to go over some resources. We have a book by Kate Gregory, who's with us today in the back. We have channel line videos both on C++ AMP and the vectorizer, stuff that Jim talked about. The open spec that I talked about is at this link. We have a forum where people can ask questions about C++ AMP. And then finally our blog, which is a great source of information not only about C++ AMP, but also PPL and the vectorizer. So thank you for your time. I appreciate it. And I'll let Jim wrap up with this slide.
Thanks.
Thank you.
All right, so I want to close and just summarize on one key point at least. We covered a lot of ground, but there's one key takeaway I hope everybody walks away with, and that is a realization of how much hardware is out there now to exploit. And if you think about it, this is the roadmap from Intel, and that's where we are right now with Ivy Bridge. Now, Haswell's about to come out for next year. We've already got preliminary parts on campus. That's a major reboot of the instruction set, and it's got 256-bit vectors for both the floating point and the integer sides. And then when that gets shrunk, they'll be using the 14-nanometer process. And so the chip I showed you, Ivy Bridge, was made with the 22-nanometer process, and this isn't far away. So this is just to further emphasize that there's going to be more and more hardware there to exploit, and it's going to be incredibly inexpensive. So with that, I just want to leave it to a few minutes just for some questions, if anybody has any questions. Yeah. The Tegra chip will actually do that. We failed the IQ test on that one. He was asking whether or not, if you say you're in a power savings mode, will you still light up all 4 cores, basically? Would that be a right characterization? Yeah. All right, so what I'm trying to do is go back to the picture. And you were talking specifically about that part, right? So as far as I know, what happens is one of the patents in this chip is that it'll actually, the hardware will sense that you're basically trying to light all 4 of these up, and it will effortlessly transition from this to 1 to 2 or to 4 cores, and then as soon as they're done, it'll go back to this idle loop with like almost 0 overhead. So I don't know exactly anything else with regard to the OS overriding that at this point. Yes?
Is there any movement on sort of like Apple implementing C++ games?
I'm going to leave that to you.
I don't have anything to announce, and Apple doesn't necessarily share their plans with me.
But, the open specification really is open, which means, anybody can can implement that spec royalty-free, you know, no strings attached. So we're encouraging everybody to do that.
While debugging, how about visibility into the threads on the GPU? Do you get to see what threads are doing?
Okay, so the question was, what's the debugging story for C++ AMP? It's great, I dare say.
It actually is.
Yeah, it is really cool. So you can debug those parallel for each loops, and there is a threads view, a GPU threads view that's very scalable and will show you variables across all the threads you have in flight. And you can do that on the software emulator, and parts are now coming out from NVIDIA and AMD that are debuggable, so pretty soon you'll be able to do hardware debugging as well.
There was actually a good session on that last year at Build. I probably watched that video online.
Yeah, that was probably by my, yeah, that's true, by my colleague Daniel Moth, who did a session at Build last year.
Hi.
Two questions, please. First is, with PPL, the schedule, is it what Intel used to call user mode scheduler? Is that what you refer to? That PPL?
Is it built on the user mode scheduler?
Yeah, Intel has a threading built-in block, and I think there is a lot of common with PPL.
Yes. So before I did C++ AMP, I was the dev lead for PPL. We worked very closely with our friends at Intel. We actually shared some code, worked very closely on it. And if you download TBB, the threading building blocks today, you'll get parallel for each, parallel invoke. They have their own goodies, so we have some of our own goodies, but we collaborated very closely on that.
Yes, but the schedule that you mentioned, is it what evolved from user mode schedule, what Intel used to call, right?
The scheduler is what they call dynamic work stealing, and the overriding thing that looks for whether a worker is available to steal work from you. We developed that.
So it never goes to kernel mode.
No.
Switches in user mode.
And in fact, there's a global variable. You can actually go see this in the code. You can crack the templates if you want to and go down, and you can actually look for a global variable called, I think it's worker n, and you can see that the check for that is not even atomic. It's not. That's why the scheduler is so scalable. The only atomic update occurs when you do have a worker and you are going to do some work stealing to dynamically distribute work to another thread.
Thank you. Second question, with both PPL and AMP, is there a runtime check if it's old CPU which doesn't support it? So
In PPL or in the vectorizer?
both.
The PPL doesn't do any runtime checks. When you say go for it, that's what the template.
Let's say I have old Pentium which doesn't support scalability.
You have what?
Old Pentium processor, so I built for.
Oh, well, when we compile the C++, there'll be a runtime check for the advanced instruction sets, but by default, we are generating SSE2, and if the chip doesn't have SSE2, then that binary won't run on it. But we did check the market to see how many chips are out there without SSE2, and it came up to be an incredibly small number. The x64 chips came out right away, first with 64-bit, with the SSE instructions in them. So you're talking about something pre-2002?
Maybe, yes.
So
And for PPL,
you have bigger problems then.
For PPL, it does ask how much parallelism is available, how many cores are available. So it'll run on one. Even if you say parallel 4, it'll run on one core if that's all that's profitable.
No, wait a minute. So did C# disappear? Is that a correct summary? So no. So, in fact, what we're doing, we're trying to bring this technology to that platform as well. We just brought it up in native C++ first.
And you can get it C++ AMP through interop. It's pretty straightforward.
Sir?
In your example
You only get 4. Oh, then we'll only run it on a single core. The threads will be forked, but they'll run sequentially on that one core. Yeah, you absolutely can, and we do. So when you do N, we check. All right, so everybody, oh, one more?
So the automatic parallelization,
Yeah.
which I guess runs even if I don't physically ask for it, what happens if my machine, I'm actually like process level parallelization running 4, single threaded processes flat out, and, it wouldn't actually be worthwhile to try to pass them another course because they're busy. Does it detect that, or does it just try to load up those other cores anyway?
Oh, that's a really great question. So no matter what construct you use, you're going to have that problem. So what you're talking about is whether my application composes, right? Have I oversubscribed the machine? And this is one of the places where, I don't know why they don't talk about this. They've really improved the scheduler in Windows 8. Okay, it's really hard to overwhelm the scheduler in Windows 8. That's an aside. You still can, as an application developer, oversubscribe the machine, and it's your job to worry about whether the applications compose. Okay? So if you're Shell Oil and you want to actually, you're drilling for oil and you bought a 32-core machine and you want FFTs to go on all 32 cores 100%, you're not going to be excluded, right? Whereas if you're writing an application that maybe does the cartoonizer and you're on a machine that's being shared with a bunch of people, you're going to have to worry about how that's going to compose. There's no magic bullet for that problem, at least that we've found.
You mentioned there was a log files to identify like places where the compiler gave up. Are there other profiling tools that you could say, okay, this is where you probably ought to think about using these constructs or things like that. Or do we just have a log file?
Well, the log files will tell you statically at compile time what we were able to figure out could go parallel or could go vector. What you want to do, though, is you want to go back and you want to profile your application to find out what the hot loops are. And then if you are getting, you can use Visual Studio or you can use VTune from Intel, right? Because there's different levels of profiling. And this is another critical point, which is that you really, really, really want to worry about whether you're blowing out the L3 cache on that chip. So that actually means that you want to look at some hardware events. So if you go parallel, if you're going vector and parallel, you're really going to pound the cache, right? That's where the point of contention goes. And so usually if there's a problem and you're not getting the performance you want, it's because you aren't using the right scheduling strategy, or you've caused some kind of thrashing in the cache, or you're blowing out the TLBs. Those are usually the 3 things that matter.
There's some to see the memory moves between the GPUs and CPUs. Pretty much you choose that automatically right now. I mean, what if I write code that's thrashing across the moves? How would I discover that?
You can discover that in the concurrency profiler. You can see markers when memory got moved to the GPU. You'll be able to see that. So one more question, and then I think we're going to hang out afterwards if you want to ask us individually. So this guy's been waiting for a long time.
Oh, sorry.
I briefly looked at OpenCL and Direct Compute, and I see you pass it with your source code directly in. Our algorithms to process their data are pretty much our IP, and we don't want to just give that away to anybody to replace the DLL with something. Save our code to disk. What does AMP do?
So C++ AMP will actually, okay, yeah, where does my C++ AMP go, and can users look inside my binary and find my proprietary algorithms? So what it does is it compiles it down to DirectX bytecodes. They're put into the DLL just the same way as a function x86 body is put in a DLL. I suppose you can disassemble those just as well as you can disassemble x86, but it's better than shipping source, which is what you're stuck with OpenCL. Because Direct Compute is lower level, and if you're programming to that level directly, you need the source on the disk to compile it. We compile it at compile time and put the compiled result in the binary. All right, so we're going to hang around afterwards if you want to ask questions.
Thanks a lot, everybody.
Thank you.